Welcome back. Today we'll be covering analysis of variance, or ANOVA. Last week we talked about t-tests. We're doing the same thing with ANOVA, except this time we are comparing the difference between more than two populations. Now, an ANOVA can be used to compare two populations, but it's not limited like T is to two populations. You can use ANOVA to compare 3 different groups, 4 different groups, 5 different groups, 10 different groups, 100 different groups, although understanding what it means with 100 different groups might be a little tricky. But ANOVA is great because you can compare more than 2 groups on certain scores. All right, so first we'll talk a little bit about the logic of ANOVA. The logic, I'm going to introduce where the numbers come from. Basically, you have all the tools you need to calculate the numbers that go into calculating ANOVA and doing the test. So we're not going to go step by step through each number, but I'll kind of give you a hint what the differences are from the t-test to the ANOVA. And then we'll talk about what ANOVA doesn't tell us, because the ANOVA doesn't give us all the information you need. There's a few steps beyond ANOVA post hoc tests that are needed to interpret differences, because the ANOVA tells us an overall difference between all of these groups that we compare, and then you have to run individual tests to look at individual group differences. All right, so some of the key questions that we're asking with ANOVA, you want to think about what type of data am I using? You probably thought you wouldn't have to think about variable types ever again, but yep, you still need to know variable types. And with ANOVA, you're using one nominal variable, just like with the t-test, the independent t-test, but this nominal or grouping variable, it can have 2 levels, it can have 3 levels, 4, so it's not limited to the 2 levels, so 2 or more levels of this nominal variable. And typically people say ANOVA is used when you have 3 or more levels, because the easier t-tests can be used for 2 levels. Even though ANOVA can be used for 2 levels, when you have 3 levels, that presents the problem that you can no longer use the simpler t-test. You now have to use ANOVA. So 3 or more levels, you're going to have to go with ANOVA instead of a t-test. And you also have one continuous variable. So just like before, when we used the t-test we were testing the continuous variable, differences on that continuous variable between 2 groups. And now we're testing the difference on that continuous variable between 3 groups, or between 4, 5, 6, whatever you choose with the ANOVA. And our question of interest with the ANOVA is, are the differences between these 3 plus population, are there any differences between the average on that continuous variable between these different groups of your nominal variable? So we're asking the same question about the population. We're always hypothesizing about the population, but we don't have information from the entire population. You have to use sample information. So you look at the sample differences, you go, okay, are the differences between all the samples big enough that we can include the populations, whether it's 3, 4, 5, 10, 100 populations, whether the populations are truly different. So we're using curves again, probability, the shape of the F distribution, the F. When you're running an ANOVA, we no longer have T, we have F. So F is the test statistic that you use for ANOVA, and there's no longer a T distribution. We now use an F distribution. It has a little bit of different properties than the T curve, because of the way that ANOVA is calculated. All right. So why we need ANOVA? The t-test is limited. You can only compare 2 groups. Now, if you think about looking at differences, so we're asking with the t-test, are there differences between 2 different groups in the 2 different populations on this continuous variable, the means of these 2 groups? So we subtract one from the other. But if you have 3 groups, can you subtract one mean from the other? What do you do with the third mean? Do you subtract it from the first one or the second one, or do you rearrange it? So it doesn't work. Okay, you have 3 different groups, 3 different means. You can't use a t-test because simple subtraction of one mean from the other doesn't work. ANOVA is brilliant in the way that it uses the variance. So instead of subtracting one mean from the other, you calculate the means of each group, and then you use those means as if they're scores and calculate the variance of those means. If those means, say we have 3 groups and they have 3 different means, and if the variance of those means is really big, that means the difference between the 3 means of those groups is huge. If the variance is really small of those means, then we know that the variance of those means is really small. So we're comparing the variance, and that way you can throw in a 4th group, because with variance you can plug in, remember, variance is the squared average deviation from the mean. Okay? So we're using variance instead of differences to test whether these groups are the same or different. So it's the same logic, but different calculations. It's a great way to be able to add in more groups. The t-test was using the logic behind the z-curve, using the z standard normal curve or variance of it for the t-curve based on drawing means and mean differences. Now we're going to use the same logic except with variance. You square the values, so you're never going to end up with a negative value. So our F distribution, and unlike the t distribution, is not a normal curve. The F distribution will never be below 0 because you square variance, and so you're always going to end up with squared values that are positive. So the F distribution, it goes kind of to the right, it starts at 0, and you can only go one direction with the tail. So we're not going to have the two tails for testing with ANOVA because there's only one tail on the F distribution that we use to compare our variances between the means to. Okay, but we're still going to use the same idea. What would the distribution of the variance of all these means be if the null hypothesis was true, just like we did with the t-test? So ANOVA is based on estimating variance of the population, but there are a couple different parts of variances that we estimate. You can't just estimate the variance of the means, because how do you know if the variance of the means is big or small? You have to look at the variance of those means compared to the standard error, or the variance of those means that you would expect to get if you sampled over and over and over and over from a population where all those means were identical. So you do have to estimate the within group variance first. So just like you've done before, you estimate the variance divided by n-1 when you calculate this to estimate how much variance is there within the population to begin with. Because if a population has huge variance, you expect your samples or your sample means to vary more. If your population has a small variance in all the scores, you expect your sample means to vary less. So you have to know first, what does your population look like? How big is the variance within your population, so that you can expect to get certain variances between your means just based on sampling error, or know whether that difference between your sample means, the variance of those sample means, is based on true differences in the population. So you estimate the within group variance, and then you have to estimate the between group variance. And so there are two different variances we do here: the within each group variance, and then which is how far each score varies from the own group, okay, the mean of that own group for each of the individual groups, and then the between group variance, which is how far all of the means vary from the grand mean, the overall mean. Now your F statistic, so F is similar to T, and just like T, just like Z, we always are looking for the difference on the top. So on the top of your F statistic will be the difference, but now instead of subtracting one mean from the other, we take the estimate of the between groups variance. So the variance between the groups, and then the bottom of your F statistic will be the within groups variance. So that's the estimate that gives us the error we're expecting to get. So how far the scores are spread out so that we know how far our sample means should vary. The top is the difference between the sample means in terms of how much they would vary just by chance or sampling error. So F, the way we calculate this, let me draw an example for you. If we are looking at three different groups, okay? Three different groups, we have group 1, group 2, and group 3. Okay? Now say that we have three different groups, and you could go back to our example we used last week about the kids reading books. Maybe this is the time that they took to read these books, but now we've added a group that reads books with their names and their friends' names. So we have kids who've read books that are just the general books, and then we have their own names, and then we have a group that reads own plus names of their friends. So we have these three different groups, and we're comparing reading times, how long it takes them to read this book. And now the population may have a difference between the means, but it's also going to have a spread within each group. So you might have some kids who read the book with their own name and their friends' names, and they scored higher than someone who read just with their own name. So when you're sampling from these populations, you might draw a sample here or here or here, and so you're looking at what's the likelihood of getting a sample from populations that are identical. So if all of these populations right here, they look different, but if they were all identical, so if we had identical 1, 2, we'll say those are right on top of each other. The means are all identical, 1, 2, and 3. We're looking at what's the likelihood we would have when we draw a sample, the first mean, the second mean, and the third mean might end up like this, because you know sampling error, you're not going to always end up with sample means that are exactly the same as the population mean. You might end up with sample means like this from a population, from 3 populations that look identical. So we're going to use these sample means and treat them as scores and calculate the variance. So instead of calculating the variance of scores, the top of your F distribution is calculating the variance of these sample means. So you can take mean 1 and you take the grand mean, the overall mean of your all of your sample, subtract it from that. Mean 2, subtract it from that, square it, do the third one, square it, sums of squares, divide by n minus 1, or the degrees of freedom minus 1. So here, instead of dividing by n minus 1 like you would when you're calculating variance, now if you're confused about what I'm saying right now, I suggest you pause the video, go back, review variance. You should be really familiar with variance and how you calculate variance at this point, because otherwise you're not going to understand what we're plugging in here in the F distribution. So once you've reviewed variance, come back and realize that now, instead of calculating variance with scores, you're calculating variance with means, pretending like they're scores, because you want to know how spread out those scores are, or how close together those scores are, because the more spread out they are, the less likely that all 3 populations are identical. Okay. So you take the scores, subtract it from the grand mean, square them, sum them, divide by, now you would typically with variance divide by n minus 1, except here we're not treating, these are not actual scores, so our degrees of freedom for between our groups comes from not n, but the number of groups, k minus 1. So if we have 3 groups, we're going to divide by 2 when we're calculating variance instead of dividing by the n. Now when we're calculating the error part, the within groups estimate, that we will use our n minus 1 for each group. All right. So when we are hypothesis testing with the ANOVA, or with our F distribution, our null hypothesis is always that the mean, or mu, of population 1, 2, 3, or however many populations you're comparing, that the mean of each of those populations is identical, just like the drawing I just showed you. Mu1 equals mu2 equals mu3. That's our null hypothesis. Now that's not what we're interested in. We're hoping that we find, that the effects of the books, putting their names in it changes it, or gives us something worth knowing. But that's what we test as the null hypothesis. So can you guess what the alternative hypothesis is? The alternative hypothesis is if the null hypothesis, let's go to our drawing. So here's our null hypothesis, is mu1 equals mu2 equals mu3. Our alternative or research hypothesis is that mu1 does not equal mu2, does not equal mu3. Simple enough. So our alternative would be that these aren't all equal, that one population is different from the other populations. So we're testing this by our sample information, how far apart our sample means are, how much our between groups variance varies in terms of within group variance. All right. So now let's think about some logic behind this test. If the null hypothesis was true, if it was true, all populations have the exact same mean. Okay? So if you were to calculate the variance of population means, it would be 0. Okay? But sampling error, you're never going to get the exact same mean for your samples as for the population. So if the null is true, any variation among your sample means, or between, among is used the same as between, any variation between your sample means is only due to sampling error. Okay? That variation you see, so the variation should be pretty small. It should only reflect sampling error, or luck of the draw. The small differences between your sample means, if the null is true, only reflects sampling error. Okay? If the research hypothesis is true, so that means the null is false. Now, the null hypothesis is false, your alternative or research hypothesis is true. So remember what this means. This means the population means are different. Then this would indicate that variation among your sample means, so when you draw sample means from these different populations, not only will you have sampling error in there, but you should also be reflecting true differences between those populations. So when you draw from 3 different populations, you should expect that your sample means will vary more than when you draw from identical populations and all you have is sampling error contributing to that variance. So here's a great picture. This picture shows three means that are identical in the population. And it shows that if you take three different samples from those populations, so this is A, look, I'm looking at column A right now. You see three populations and the spread of the scores in that population. But the first population, you draw a sample mean, and it's a little bit lower than the second population sample mean that you drew. And the third population down at the bottom, you drew a sample from, and it ended up in between the first and second. So you have three different sample means. One's a little bit lower than the other, but they're all pretty close together. Now, why are those sample means different? Because your samples, they only include 1, 2, 3, 4, 5, 6 scores in each of them. So you have 6 scores, six scores in each of them. So you're not including all your population information. So it's just luck of the draw, sampling error, the sample you happen to grab out of that population. Now, the difference between those is small, but it doesn't reflect differences in the population, because population 1, 2, and 3, they all look identical. So that just represents sampling error. Now, the second example shows you three populations that are different. So you can see population 1 and 3, the first top one and the bottom one, are pretty similar, but the second one, the middle population, is higher than the first and last one. So the populations differ here. Now, the means you draw from those, you see the first one and the last one are pretty close together, but that middle one, it's pretty high. Now, could you have drawn a sample mean that was down near the others? Yes, but since the actual population's higher, it's more likely that you end up with a sample mean that's even higher than before when they were all identical. So this is to show you that when the populations differ, your sample means, the variance of those sample means, should differ more. Your mean should spread out more than when the populations are identical, because if the populations are identical, the differences or the variance of your sample means is small, because all it reflects is sampling error. The second example, where the populations are different, the variance between your sample means reflects sampling error and true differences in the population. So this is a key. This is really key to understanding ANOVA, this picture here. I love this picture for illustration purposes. Now, do we in reality ever know whether the populations are all lined up having identical means or different means? No. All we get is our sample data. But if I had shown you just those sample means from column A and the sample means from column B and asked you which one do you think has different populations, you go, wow, the B has a higher variance or a higher spread of your different sample means, and you'd guess that B, the populations were different, where A, the populations were probably the same because the means are all pretty close together. So that's the logic behind the ANOVA. Now, here is another table that really just illustrates where the variation comes from. Where does variance come from if the null hypothesis is true, or if the research hypothesis is true? Now, if the null hypothesis is true, the variation within the population comes from the within groups estimate reflects variation within the populations, and the between groups estimate also reflects variation within the population. The difference here is that when the research hypothesis is true, so when the populations are all different, then your variation within the populations, so your within group estimate of the variance of the population reflects within group and between group estimates, but it also reflects true differences between the population, variation between the population. So you should see when your research hypothesis is true, or what you should be rejecting the null, you should see more variance between your sample means than when you're not rejecting the null, or when the null is false, excuse me. All right. Now, when you calculate F, because you're taking the variance of the means and then dividing it by the variance within the groups, the estimate of the population variance, assuming the null is true, you're going to then take this F value and compare it to the F distribution, which is shown on here. Now, the F distribution, as I told you, starts at 0, and it makes this curve, and it changes depending on your degrees of freedom. And now this is where F and T differ. F has a numerator and a denominator, degrees of freedom, because you're using two different sets of variances. You're doing variance of the means, how far the means are spread compared to how far the means are spread from the overall grand mean, and then how far the scores within each group are spread. Okay, that's your within groups variance. And so because you're comparing both of those, you'll have 2 degrees of freedom. Your numerator degrees of freedom is the number of groups you are comparing minus 1. And so let's go to the drawing board. When you're looking up F in the F table, your critical cutoff value, you have to have 2 degrees of freedom. The numerator degrees of freedom is K minus 1, or the number of groups you're comparing minus 1. So here, if we're comparing 3 groups, you do 3 groups minus 1 equals 2. That's your numerator degrees of freedom, 2. Now, your denominator degrees of freedom is similar to the total degrees of freedom when doing an independent t-test. So it's the n in each group minus 1. So if you have 50 in each group, or let's use a smaller number that makes it easier to calculate. Let's say you're comparing 3 different groups, and each group you draw a sample of 5. N equals 5, n equals 5, and n equals 5. Your degrees of freedom for this first group is n minus 1, 4, the same for this one, and the same for this one. Your total degrees of freedom here is 4 plus 4, 8 plus 4 is 12. So your denominator degrees of freedom here is 12. So it's the total degrees of freedom, the total score, so the total n, your total n, 5, 10, 15, minus 1 for each group. Okay, does that make sense? So it's the n minus 1 for each group is your denominator degrees of freedom. So you would end up with a numerator and a denominator degrees of freedom here. And typically when it's written in research, they write F and then in parentheses 2, 12. That means your numerator degrees of freedom is 2, your denominator is 12. Now let's take a look at the F table in your book. You may not be able to see this on here, but when you are looking up critical cutoff values in your F table, you are going to want to first look for, here's our T table. So here's our F table, and you can see it has this different distribution, but you first look for your numerator degrees of freedom up at the top. So our numerator degrees of freedom, we said was 2 since we were comparing 3 groups, so you go over 1, 2. And then you have to look down here on this column for your denominator degrees of freedom. Our denominator degrees of freedom was 12, 15 is the closest, so that's what you would stick with. Here you go over, and it also gives significance levels 0.01, 0.05. Now you don't have 2 tails in here. You can't do a 2-tailed test with an ANOVA because there's only 1 tail in the distribution, but you use the closest number to your denominator degrees of freedom. Let's say we were using alpha 0.05. Your cutoff here is 3.68. So what that means is you draw onto your distribution, you would draw 3.68 is your F cutoff. So in here, and the distribution doesn't go beyond here, it stops there. So you know anything that goes beyond that 3.68 cutoff, you are going to reject the null. Now you have to calculate your F value. You plot it on here. Once you've plotted F on here, if it's out here, you reject the null. If F's greater than 3.68, you reject the null. If F is below 3.68, you retain the null and say, no, the variance isn't big enough to conclude the populations are different. All right, so now there are a couple terms you should know when you're calculating F. SS is sums of squared deviations. You should know that from what we've done in the past. With the ANOVA, there are sums of squared deviations of the mean, of each mean when you're doing the between groups variance, the top part of your F. It's the sums of squared deviations of each mean from the grand mean. So you take the difference of the mean from the grand mean, square it, remember that. DF is the degrees of freedom. I already told you there's 2 different types of degrees of freedom. So when you're doing the top part of the F value, you'll do the sums of squares divided by the number of groups minus 1, because that's what you're finding the variance of, is those means for the groups. And then the MS is that sums of squares divided by the degrees of freedom. Okay, so that would be your numerator, MS. And then you also need your denominator of your F value. The denominator is your within group variance estimate. So it's each score. Let's go to the drawing board again. So it's the score with each score within the group, how far it varies on average from the group mean plus how far each score varies from this group mean, plus how far each score here varies from group 3 mean. So if you add up all of the variance here and the variance here and the variance here, that's what goes on the denominator of your F. And the MS, or the mean squares, is your estimate of the population variance. So you would take the average of all of these variances and divide by your degrees of freedom. So you have to use the degrees of freedom for total. So it's the total n in all of these groups minus 1 for each group. Okay. So hopefully that's making sense, that you're using all of the scores to calculate the denominator of your F. You're only using the means, the differences or the variance between the means, to calculate the numerator of your F value. Once you have the MS between the three groups and the MS within the three groups, then you divide that between divided by within to get your F value, your F ratio or your F value. And here's a nice table. I suggest you make this as you're doing your calculations. You put the sums of squares between on the top, degrees of freedom between, or your numerator degrees of freedom on the top. How many groups were they comparing here? You know the numerator degrees of freedom is 2, so that means they were comparing 3 groups. Okay? Then your within estimate of sums of square deviations from each of those group means. Divided by the degrees of freedom within. Your degrees of freedom within is your denominator degrees of freedom. So it's the total that they had, the total n in all of these groups. So you know if they were comparing 3 groups and their degrees of freedom was 12, they took away 1 for each of these groups, they'd have 12, 13, 14, 15 individuals that were in this study. And then their total degrees of freedom is the numerator and denominator degrees of freedom added together. So it's the total n minus 1, just like you would have calculated back in our one sample t-test degrees of freedom. Now, the MS, or the mean square, is the sums of squares within divided by the sums of squares within degrees of freedom. So you just take MS within 43, or sums of squares within, between, or the between the groups or among the groups. So 43.35 divided by 2 equals your mean square, 21.68. And then you go down to the next row, and within you have 64 is your sums of squares. You divide that by your degrees of freedom within 12, and you get a mean square error of 5.33. Now, once you have both of your mean squares, then you can calculate F. The mean square numerator, or between the groups, is 21.68. You divide 21.68 divided by 5.33, and you should get your F value of 4.07. Then you have to take that F value. That's your test statistic, just like T was before. You have to plot it on your F curve, see if it passes or doesn't pass your critical F value. If it passes, you reject the null. If it doesn't pass, you do not reject the null. So ANOVA tells us whether the populations, remember our null hypothesis was that the means are all different or the means are not different. So it either tells us, yes, the means are significantly different, that they differ enough that it's not just chance, that the populations probably differ, but it doesn't tell us whether mean 1 differs from mean 2, or whether mean 1 differs from mean 3, or whether mean 1 and 3 are the same and 2 is different. And so just running an ANOVA isn't good enough. You then have to do follow-up tests. The follow-up tests tell you exactly which group differs from the other. So doesn't this sound like multiple t-tests to you? It does, but remember I said we had a problem with multiple t-tests because you end up with an inflated type 1 error like I discussed last week. So in order to deal with this, we don't run multiple t-tests. We run follow-up or post hoc tests like the Bonferroni correction. And what comparisons like this, there are several different types of these, but what the comparisons do is essentially they lower your alpha level. So I'm going to show you how to do the Bonferroni, give you one tool you can use as a follow-up comparison post hoc test. So here is what we do for the Bonferroni. You just take your overall significance level or your alpha level. If it's 0.05, if you've left the 5% in the tail, and you have 5 comparisons, then you divide that 0.05 by 5, and now your significance level that you're only going to reject if you go past the 0.01 level. Okay. So you're just essentially making your test fit. Now you have a 5% chance of error, but you use the 0.01 cutoff on your F table, the 0.01 cutoff in that a little bit further out in the tail. So if it fell at that 0.04 cutoff, you're not going to reject the null, only if it goes past the 0.01 cutoff. And you can go look through the examples. Here's another one. If you're only running 3 tests, you would use 0.05 divided by 3. You'd have the 0.017 cutoff. Now your F table that we have in our book only gives you the cutoffs for 0.05, 0.01, and 0.10. So you would need a statistics program to run these if you have these different cutoffs that would actually just adjust it for you in these statistics programs. Here we're a little bit limited by just using the table, but I think it's great to work through these, get the concepts, use your table to figure out before you start using statistics programs that do it for you, because you can plug anything into those, but you don't necessarily know if you're using the tools correctly until you understand the concepts behind them. All right. Last thing today, effect size for ANOVA. The effect size we use for ANOVA is r squared. And the calculations for r squared, you just take the sums of squares between. So that's, remember the sums of squares between how far the means differ from each other, how far they vary, the sums of squared variations of those means, divided by the sums of square total. So it's giving you the proportion or the percentage of variation of the total variation that's due to the means being different, or the variation between the groups. So that's your estimate of effect size, is the proportion or the sums of squares between divided by the total sums of squares, the total variation that you have in your sample. That's an estimate of the population. And then there's an alternative way to calculate it right below that, where you just use the calculated F and multiply by the degrees of freedom between. So remember, your degrees of freedom between is your number of groups minus 1, divided by F times the degrees of freedom between. So that same top part plus the degrees of freedom within. It's a little bit simpler when you're doing the calculations. All right, so we've covered the basic logic of ANOVA, the differences between t-test and ANOVA, what you need to know about those differences. Post hoc tests, Bonferroni is one of the post hoc tests that you now know how to do, and the effect size for ANOVA. So go ahead and practice this. Now you should know that you have to take everything you've known up to this point, how to calculate means, how to calculate sums of squares, how to calculate variance, and you're just making some minor adjustments to fit the logic of this testing. You're using a new distribution, the F distribution, and your F statistic instead of a T or a Z statistic. So it's all the same logic, the same types of hypotheses, just new values, new numbers to work with. All right, if you have any questions, feel free to ask, and I will see you next time.